Okay, so welcome back, and now what we're going to do is we're going to talk about some application problems, because this is where parametric equations become very helpful. Because a lot of times we can describe the path that an object takes that is launched, right? But it's completely different it's a completely different question, say, where was the object at a time after it was propelled? For example, if you are looking at a baseball game and you want to know, hey, when the ball leaves the pitcher's hand and you want to plot a curve, right, that not only gives the trajectory of the ball, but it also gives the time, right? So the position of the ball at time t. Or let's say you want to look at the curve that the ball makes, the trajectory of the ball, when it leaves the bat, right? When the batter hits it, okay? Knowing the angle of trajectory, right? And the parametric equations, we can not only plot the curve, the trajectory of the ball, but we can also say, hey, where was the ball at any time along the curve, okay? So for example, when we deal with these types of situations where you're propelling an object at some angle, okay, of elevation. So what we have is something that looks like this, where we've got a position here, right? And the horizontal, and we're launching something at an angle theta to the horizontal. Okay, we want to know what the trajectory of that is, but we also want to know, hey, at some time t, what's the position of that object? Okay, and so again, using what we know about physics, it's going to have some sort of parabolic shape, right? Due to gravity, right? It's not going to stay up in the air forever. It's got to come down. So it's going to have this nice little arc shape to it. Okay, and the parametric equations that are used to model the x direction and the y direction is given by these two equations, where this is v sub 0 is the initial velocity, right? T is time. G is the gravitational constant. It's either going to be given in feet per second squared, which would be 32, or it's going to be given in meters per second squared, which would be 9.8. So again, depending on the units given, that's going to determine what value you use. And then of course, height is the initial height of the object. Is it at ground level? If it was at ground level, h would be 0. Okay? Or let's say it could be something that's launched at above ground level. Okay? Or something launched below ground level. Okay? So again, but these are the two parametric equations that would be used to model not only the path of the object, but also model the position of the object over time. Okay? So now, using these two equations, let's say we have an example here, and it says, solve the problem presented at the beginning of this section. Okay, so what's the example? It says, so we're talking about baseball. So we're talking about the motion of a baseball. It says, does the batter hit the game-winning home run? So what's the situation here? Well, the situation given is it is the bottom of the 9th inning, there with 2 outs and 2 men on base. The home team is losing by 2 runs. The batter swings and hits the ball at 140 feet per second. Okay, so that's the initial velocity of the ball. 140 feet per second. Now, since it's given in feet per second, the gravitational constant that we're going to use is going to be 32 feet per second squared, because we need the units to match. Okay? So that's the acceleration due to gravity in feet per second squared. Now, the ball comes off of the bat at an approximate 45-degree angle. Okay? Or pi over 4, if you want to do it in radians. It says, how far will the ball travel? Will it clear the fence for a game-winning home run? The outcome may depend partly on other factors. Of course, we're using a simplified version of this because, of course, there's wind dynamics, drag, lift, the ball. There's all kinds of things that make this a much more complicated problem and a much more interesting problem when you get to calculus or differential equations. Let's see here. But we're going to assume that there's negligible wind and negligible friction or resistance. So, what other information is given to us? Let's look at the problem. Okay, so it says here, and it makes contact 3 feet above the ground, right? So again, you're swinging at the ball's not coming, you're not golfing, right? So the initial height of the ball when it hits the bat is going to be 3 feet. Okay, so now, let's see here. It says, find the parametric equations to model the path of the baseball. Okay. Well, we've got the two equations. All we have to do is substitute in what we know. So the initial velocity is 140. So this is going to be 140 cosine theta. Cosine of 45 degrees, by the way. Or pi over 4. I'll just put pi over 4. Okay. And then G here's 32. We're going to put in 32 feet per second here. And then, of course, this is 140. Okay, and then H is 3. And I think that's it. I think we got everything. Oh, of course, this is pi over 4. All right. Now, I'm going to simplify this. Okay, so cosine, so let's, again, we want to find our models, right? So cosine of 45 degrees is, what? Square root of 2 over 2, right? So this is going to be, if I simplify this, this is going to be 70 times the square root of 2 times t, right? Okay, and then y is going to simplify, this is going to be 16 t squared, and then sine of pi over 4, that's going to be the same, so this is going to be plus, this one's going to be again 70 times the square root of 2t plus 3. So those are going to be the two parametric equations that's going to model this situation. Okay, so now, the next part says, where is the ball after 2 seconds? Well, now it's just a plug and chug problem. Okay, so now that we've got these two, now all we have to do is plug in 2 for t. And so, x of 2 is going to equal 70 times the square root of 2 times 2, which is just going to be 140 times the square root of 2, which is going to give approximately, what? 198 feet. So, after 2 seconds, the ball is 198 feet from the pitcher in a horizontal direction. Okay? So 198 feet in the horizontal direction from where the ball contacted the bat. Now what about y sub 2? Okay. So y sub 2 is going to be 16 times 2 squared plus 70. Oh, well, okay, I'm just going to. So 70 times the square root of 2 times 2 plus 3. And so this is going to be 64, right? 64 plus 140 times the square root of 2 plus 3. And so this is going to be approximately equal to, oh, hold on a second. I forgot my negative. This is negative, negative, negative. So negative. So this is negative 64. So that's going to be approximately 137 feet. So basically what this is saying, it's 137 feet above the ground. Okay? So the ball is 137 feet above the ground and 198 feet from the batter, or at the time that the bat struck the ball. Now the next question is, how long is the ball in the air? Okay, now, how do we handle this one? Okay, so let's go back here. I'm going to erase this stuff here. Okay, now, that means y has to be 0. Okay, so what happens when y is 0? Well, we have to solve that equation when y is 0. Okay. And we end up with a quadratic equation to solve, right? Because this is going to be what? Negative 16 t squared plus 70 times the square root of 2 t plus 3 is equal to 0. And so we've got a quadratic equation here. And so in this case here, we would use the quadratic formula. So we would use t is equal to b, which is going to be, it's going to be negative b, which is going to be negative 70 times the square root of 2 plus or minus the square root of b squared, which is going to be what? It's going to be 4,900. Well, let's do this. So it'd be this whole thing squared, which is going to be 4,900 times 2, which is going to be 9,800. So this is going to be 9,800 minus 4 times negative 16 times 3, okay, over 2 times negative 16. And so we can simplify this a little bit. I'm not going to simplify the whole thing, so it's going to be 70.2 plus or minus. This is going to be the square root of 9,800 plus, what? 64 times 3, which is 180 plus 12. No. Yeah, 180 plus 12, so 192. Right? So this is going to be 64. And 64 times 3 is 180 plus 12. Yeah, 192. Over negative 32. Okay? And so what do we get? We're going to get t. We're going to get two values for t. Okay? The negative value, we're going to actually get a negative value, okay? And we don't want the negative value for t. Okay? Because that doesn't make any sense. We can't have negative time. So the other value of t we get is approximately 6.2 6.22. So it's going to be approximately 6.22 seconds. Approximately 6.22 seconds after the ball is hit. So the ball is going to hit the ground approximately 6.22 seconds after it contacts the bat. Okay, so that answers that question. And the final question they're asking is it a home run? Well, the thing is we don't know. Okay? Because they don't give us that information. Because we don't know how far it needed to be hit. Right? Because again, we don't know the baseball field. But let's assume something. Let's consider. Okay? And again, the home run changes, or the distance that you have to hit changes from field to field. Okay, so but for simplicity's sake, let's assume that the outfield wall is 400 feet from home plate in the deepest part of the park. Okay? So, now let's also assume that the wall is 10 feet high. So in order to do a home run at 400 feet, right? So let's all the way to 400, let's say 400 feet away, the ball is going to have to be higher than 10 feet above the ground. Okay? It's going to be has to be at least 10 feet above the ground when it's 400 feet away. Okay, so guess what? At this point, we're going to what are we going to do? We need to solve for basically we need to find we're given X and Y, and so we're going to need to find the height of the ball the moment it was 400 feet. So what are we going to do? Well, we're given the value of the distance, right? Well, we can plug in 400 for X and solve for T, right? And then we can plug in T here, right? That time in here, and find out how high he was off the ground. That's what we can do. Okay, so let's do that. So I'm going to erase this now that we have this. Oops. Yeah. Okay, so let's go back to the question. So we have X equals 70 times the square root of 2 times T, right? And then this one here, y equals negative 32t squared plus 70 times the square root of 2t plus 3. Okay, right? Okay, so now what I'm going to do is set this equal to 400, right? And solve for t. So this means T is going to equal what? 400 divided by 70 root 2. And this is going to give me an approximate time of what? So you can just stick that in your calculator, and we get an approximate time of 4.04 seconds. 4.04 seconds. And now what I can do is I can take this time, stick it in here, and solve for y. So now I get negative 32 times 4.04 squared plus 70 times root 2 times 4.04 plus 3. And if I stick this in my calculator, what do I get? I get an approximate height of wow, holy cow. So I get 141.8 feet above the ground. That is definitely a home run. Okay, so it is definitely over 10 feet. So yes, in this scenario, it would definitely be a home run. It would be out of the ballpark for sure. Have a great day.